All right, in this video we're going to do some practice problems for simplifying square roots. We're in practice 6.2 of Al Grosch's book Developmental Math 2. So to simplify these square roots, first of all, recognize we're talking about radicands that are not perfect squares. And we're not going to do decimal approximations here. We're going to do what we call exact simplification, which involves leaving the radical or square root symbol in. So if you watched the previous video, I did these by separating the radicand into two factors. In this first radical, I'm going to put a factor of 28. That's a perfect square, and I know that that's 4. In the second radical over here, I'm going to put the number that needs to be multiplied by 4 to make 28, and that would be 7. And since this is a perfect square, I can then take the square root of 4, which is 2, and the numbers that I left here in the not perfects, they will just stay under. So this simplifies to 2 square root of 7. If you need more in-depth explanation, you should go back and watch the actual video, the lesson. So we're going to do the same thing here. I'm looking for a perfect square that's a factor of 54. And that perfect square will be 9. 9 times 6 makes 54. Now you might think it's weird to put a 6 over here, but there are no factors of 6 that are perfect squares. So this is what we call the perfects and the not perfects. 9 times 6 is 54. 9 is a perfect square. So the square root of 9 is 3, and the numbers that were left in the not perfects just stay under. So we have 3 square root of 6. For this one, this 2 that's on the outside is going to get multiplied times anything that we can take out of the perfects. The factor of 125 that is a perfect square would be 25. And we multiply 25 times 5 to get 125. The square root of 25 is 5. That needs to get multiplied times this 2 that was out front. And that will give us 10. And then these that were left in the not perfects, they just come down. So we have 10 square root of 5. Number 4, the square root of 48. I know 48 is 16 times 3. And 16 is a perfect square. So you're always looking for a number here that's a perfect square that is a factor of the original radicand that you're trying to simplify. The square root of 16 is 4. We get 4 square root of 3. All right, this 3 is going to stay here. To be honest with you, I'm not really sure what number is a factor of 162 that's a perfect square. So we're going to go back to using the prime factors. So I'm going to put 162 on the tree, and I know that this is divisible by 2, and that will give us 81. And look, there's my perfect square right there. So this is 81 times 2. The 3 is going to stay here. The square root of 81 is 9. We multiply those together. We get 27 times the square root of 2 because these not perfects come straight down. All right, for number 6, I have 108. So I'm going to put 108 onto the tree and see if I can find some prime factors here. I know it's divisible by 2, and that would give me 54. And I know 54 is 9 times 6, so I can separate those down into their prime factors. So for prime factors, it looks like I have two 2s and 3 3s. So this is the method that I use when I'm not sure what's a factor of 108 that's a perfect square. If I break it down to its prime factors, then I'm going to make pairs of matching factors. And for each pair of matching factors, I know that they can take a square root as 1. The square root of 2 times 2 is 2. So these will come out as a 2. The square root of 3 times 3 is 3. So those will come out as a 3. And I have this lonely 3 left underneath here. So after I simplify this, 2 times 3 is 6. I get 6 times the square root of 3. Number 7, now I'm going to work with some variables. What's important to know when you're working with these variables is that all the even numbered exponents are perfect squares, 2, 4, 6, 8, and 10. The odd exponents need to be broken down. So we will take one away and make this x squared because we know that's a perfect square, but that leaves us with one extra in the not perfects. This is still x cubed because this has the invisible 1 exponent here. So this is still x cubed. We just broke it down to be a perfect, an even exponent, and one extra. Well, the square root of x squared is x, and then we have our not perfects. So x square root of x. The square root of x to the 9. Please don't make the mistake of saying this is x cubed, because we know that x cubed times x cubed does not make x to the 9, it makes x to the 6. So don't make this mistake. It's easy to make. It's a very common mistake. Instead, take this odd exponent, take one away to make it a perfect square. You take one away because the even exponents are all perfect, and you have one extra here. The square root of x to the 8 is x to the 4, and we have our not perfects as the square root of x left over. Okay, we're going to do the same thing with this one. X to the 6 is already perfect because the exponent is an even number. So we'll put that in the perfects here. Y to the 5 needs to be broken down, so we'll take one away, make it y to the 4, put the one extra over here. Now take the square root of these by dividing these exponents in half. So we'll have x cubed, y squared, and the not perfects just coming down, square root of y. On number 10, this x on the outside is just going to hang out for a while. It'll just get multiplied times anything that comes out of our perfects here. This is an odd exponent, so we're going to break it down to be one less, which would be x to the 6, and one extra. Now, this x out here is not doing anything yet. It's going to multiply times the square root of x to the 6, which is x cubed. And that makes x to the 4th. Because remember those rules, when we multiply variables, we add the exponents. And this one has the invisible 1 on it. And then we bring down these that were left in the not perfects. On number 11, we're going to do the same thing. We have x squared on the outside. However, x to the 10 is perfect. We don't need to break it up into two parts. We only do that when we have some not perfects. So we can go ahead and skip that step and just go right to the square root of x to the 10 is x to the 5. We simplify by multiplying. We get x to the 7. On number 12, we have x cubed and a y on the outside. They're going to get multiplied times whatever comes out of these perfects. With an x to the 11, since this is an odd number, we'll break it down. We'll have x to the 10 and one extra. Y to the 14 is an even exponent, so this is already perfect. We don't need to break it up. If it's already an even exponent, we don't need to break it up. So we'll keep the y to the 14 here. Now we'll take the square root of these. But first we still have this x cubed y here. The square root of this is going to be x to the 5th, y to the 7th. Now we will multiply all this together. We will get x to the 8th, y to the 8th, and don't forget to bring down your not perfects. All right, number 13, we're going to be doing the same thing, except now we've got coefficients and variables mixed together. So again, we're going to start with the perfects and the not perfects. All right, so we're just going to look at the coefficient first, then we'll look at the variable separately. So for 40, do we have a perfect square factor? Yes, we do. We have 4. 4 times what? 4 times 10 is 40. And then we do x cubed. Well, this is an odd exponent, so we're going to break it apart. to be x squared and 1 extra. Now we will take the square root of these perfects. The square root of 4 is 2. The square root of x squared is x. And these not perfects, they just come straight down. All right, on number 14, we've got a 49, which is a perfect square. You can write the 49 in the perfects, or since you already know, most of you already know, the square root of 49 is 7. Don't make the mistake of putting the 7 here. You're not trying to find the square root of 7. You're trying to find the square root of 49. If you want to skip right to the 7, write it down here. It'll be on the outside of the square root. You need to break down this y because the 11 is an odd number. Break it down to be y to the 10 and 1 extra. Now when we take the square root of these, the square root of 49 is 7. We've already got that. The square root of y10 is y to the 5th, and the not perfects come straight down. All right, on number 15, this 2 is just going to get multiplied times anything that comes out of the perfects. Factor of 50, that's a perfect square, would be 25. The x to the 6, because the 6 is an even number, 6 is an even, it's a perfect square, so we can put the whole thing in the perfects. But the y21 is an odd exponent, so we'll break it apart to be y20 and 1 extra. So we need to take the square root of these perfects. The square root of 25 is 5. The square root of x to the 6 is x cubed. The square root of y20 is y to the 10th. And now simplify by multiplying times this 2. We have 10 x cubed, y to the 10th, and these not perfects, they come straight down. All right, this is just more of the same. We've got the 3x being multiplied on the outside. We have an 81 here, which we know is a perfect square. If you want to go right to the 9, make sure you write it on the outside. Now don't be fooled. X to the 25, just because 25 is a perfect square doesn't mean that x to the 25 is a perfect square. When you're talking about exponents, only the even exponents are perfect squares. So this 25 is not a perfect square. We still need to break it down. We're going to break it down to be x24 and 1 extra. But now this y to the 100th power is a perfect square because that 100 is an even exponent. So take the square root of your perfects. We have the 9. We have x to the 12. We have y to the 50. And that's going to get multiplied times this 3x that was out front. And that gives us 27, x to the 13, y to the 50. And these that are under the not perfects, they come straight down. So square root of x. Okay, on number 17, we're going to have 4xy times anything that comes out of the perfects. So 45 is not a perfect square, but there is a factor of it that is, and that would be 9. 9 times 5. X to the 16 is perfect. Y to the 27 is not, so we'll break it apart to be y to the 26 and 1 extra. Take the square root of your perfects, and we have 3 x to the 8, y to the 13, times the 4xy that was out front, gives us 12 x to the 9, y to the 14, and these not perfects still come straight down, square root of 5y. Number 18, we have 5x squared y cubed on the outside. We have a 72. The factor of 72 that's a perfect square is 36. 36 times 2 makes 72. We're going to break up the x to be x squared and 1 extra. The y is perfect, so it can stay in the perfect. But the z, since there's only one z, it can't be perfect, because the exponent on the z is the invisible 1. There's no way to break it apart since there's only one of them, so it's going to go over here in the not perfects. All right, we're going to take the square root of these. Square root of 36 is 6. Square root of x squared is x. The square root of y, 8, is y to the 4th. Times 5x squared y cubed makes 30. X cubed y to the 7th. And these come straight down. All right, number 19. Don't be freaked out because it's a fraction, because we have that fraction rule that says whenever you have a fraction as a radicand, it's okay to break the radical up and make two smaller ones. So this is equal to the square root of 36 over the square root of 121, and these are equal. And this makes it much easier to simplify because we know the square root of 36 is 6, the square root of 121 is 11. Those are both perfect squares. On number 20, you have this rational expression here under the radical. It would be best to simplify this rational expression first before you do any square rooting. So I'm just going to ignore the radical, and I'm going to take this rational expression, 27a to the 6th, b to the 5th over 20a cubed, b 15, and I'm going to reduce this expression first. 27 over 20 does not reduce. They don't have any factors in common. So those are going to have to stay. The a's reduce, though. You have 6 on the top and 3 on the bottom, so those will reduce to a cubed, and the b's will reduce to bb to the 10th. Now we can bring the radical back as two smaller radicals in the numerator and the denominator. If we have room, we're going to do the numerator, square root of 27a cubed. All right, there's a perfect 9 times 3. The a is going to get broken up to be a squared and a, and then we'll take the square root of these perfects, and that'll be 3a square root of 3a. And that's the numerator of this fraction. So we'll write that up here on the top, 3a square root of 3a. Now the denominator, we'll do that over here. We have square root of 20 b to the 10. All right, there's a perfect in 20, and that would be 4. 4 times 5 makes 20. B to the 10th is perfect, so we can go in the perfects. And now we can take the square root of these, and that would be 2 b to the 5, square root of 5. And that will be the denominator. And just like I said in the lesson, for the purpose of this course, this is okay for right now. But we do have this math rule that says you're not supposed to leave a radical in the denominator of a fraction. In a further lesson, we're going to rationalize the denominator, but we haven't learned that yet. We'll do that in a future lesson.